Hi students, in this lecture I am going to discuss Pascal's law and Archimedes' principle. Let us see first one. So first focus Pascal's law. Let us consider a vessel which contains water. So we are taking one vessel. You can see shape here. This is now filled with water. And let us take here one piston on left side and right side. And left column having a lesser cross-section area. Piston here. And here one more piston. Suppose this area is A1 and this area is A2. This is now liquid, that is water, which is incompressible. Now see, if we apply a force, on the smaller piston, see what happens. So applying force, suppose F. Then you can see below the piston, now pressure increases by, it increases by F1 by A1. So pressure changes by F1 by A1. So just below the piston, pressure is now increased by F1 by A1. Now, Pascal's law says that this increase will be same at each and every point, not only just below the piston. If I am taking here at this point, or at this point, or at this point, or at this point, at any point in this liquid, pressure increases by same amount. That means if we produce a change in pressure at one point, the change will be the same at each and every point in that liquid. So condition number one, it is enclosed in a container. It is a closed container. And second thing, the liquid must be incompressible. Incompressible means we cannot compress it. That means density is same at each and every point. Okay. So change produced that will transmit to each and every point without any change. That means change in pressure, that value will be same. That means in this problem, means here, changes by F1 by A1. So at each and every point, pressure increases by F1 by A1. That means at this point also, pressure increases by F1 by A1. You just imagine here, we are keeping here a heavy object, or we can say this is a car. This is a car. We can say like when we're having car washing, you might have observed that a car is lifted using the same principle. Okay, so your area is now less. So even for small force, you can see F1 by A1. Since A1 is small, F1 by A1 will be large. That means change in pressure is large. Now here extra pressure. It is now F1 by A1. This pressure into the corresponding area, that is A2. That gives now force. So this force is now lifting the car. That means if you observe carefully, if A1 is very small, then F1 by A1 will be very large. If A2 is large, then force will be large. That means Here making the area very small. Here making the area very large. In that case, even for small force, we can get more force. That means with a small force, we can lift heavy objects. So this is a principle we are using in hydraulic lifts. This is hydraulic lift. So hydraulic means we are using liquids. Okay. That's what it is named as hydraulic lift. Now same principle used in hydraulic brakes. We can see nowadays in most of the cars, in most of the vehicles, brakes are basing on the same principle. They are known as hydraulic brakes. Okay. So this is now result how much of force we are get. And if you observe how much work is done. For example, this piston comes down by a distance x1. Then see work done by this force. If you are taking this is a constant force, work done that is equal to force. It is F1 displacement x1, and between these two vectors angle is 0 because x1 down, f1 also down, right? Coming to here, see how much work is done. F2 W2 that is equal to F2 into, suppose it moves up by a distance x2, then see it is into x2. Now focus how to get relation between x1 and x2. You can see if this piston comes down by x1, this is now present position of the piston. See here we are missing this part of the volume. This missing part of the volume must reflect in this part. So if it moves by x2, then corresponding increase in volume, that is A2 into x2. This A2 x2 must be equal to A1 x1. See carefully. This is a volume we are missing here. That volume must appear in the right part. Therefore, A2 x2 should be equal to A1 x1. Because the condition is here, fluid is incompressible. That means its volume does not change. Okay. Now use this result in this one. See what we get here. F2 in the place of F2, write this one. F1 by A1 into A2, that is F2. In the place of x2, in the place of x2, A1 x1 upon A2. Now see what we get. So A1 cancelled, A2 cancelled. Remaining is now F1 x1. We can say this is now input work, okay, F1 x1. This is now output, input F1 x1. Output also it is F1 x1. Means how much work is done here. Same output we are getting here. Okay. So no change. The energy which we are spending here to lift a vehicle, input and output both are same. The only advantage is here with less force we are getting more force, which is helping to lift heavy objects. Okay. Let us see statement. See the statement here. Pressure applied to an enclosed incompressible fluid will be transmitted to each and every point of the fluid without diminishing. Diminishing means decreasing. Without diminishing means without any decrease. Okay. That means whatever change is produced, the same change will be present at each and every point. Okay. So examples like hydraulic lift, hydraulic brake. Okay. There are many applications like this. Let us see now Archimede's principle. Right, focus once. What is it? Consider a body. First, take one vessel which contains liquid. Let us take this is now completely filled with liquid. So we are taking a vessel which is completely filled with liquid. It is completely filled. So now we are immersing a body into this. Now see what happens. So to make calculation simple, I am taking here one cylinder. So I am taking here a cylinder. So vessel completely filled with liquid. We are immersing one object. Its shape is now cylindrical. It is now cylindrical. Then see what happens. Initially, this volume was occupied by liquid. Now this volume is occupied by cylinder. Now, Archimedes' principle says that this cylinder, or you can say this body, experiences a force because of this liquid. And that force we are calling as buoyancy force. It is known as buoyancy force. Force by the liquid on the body. That buoyancy force is equal to weight of the it is equal to weight of the displaced liquid. See meaning of this displaced liquid. So initially this vessel was completely filled with liquid. Now we are immersing this body. So this volume was initially occupied by liquid. Now that volume is now occupied by the body. So how much volume of liquid is now displaced? It is simply equal to volume of this body, right? Now force acting by liquid on this body is equal to weight of the liquid displaced. That means if I am taking here this cross section area is A, okay? Cross section area of the cylinder is A. Its height equal to H. So how much volume of liquid is displaced? That is equal to volume of the body, A into H. This is volume of the body. This is volume of the liquid displaced. It is given weight of the liquid displaced. So I'm multiplying with density of liquid. Okay. Into G. This is giving us weight of the liquid displaced. So buoyancy force, or you can say force by liquid on this body is equal to weight of the liquid displaced. Okay. Let us see how to get this one. So here, force acting by the liquid on the curved path. It is only horizontally acting. Okay. That means by symmetry. Force by the liquid on curved part gets cancelled. Okay. Now remaining is force on the top surface and force on the bottom surface. Suppose it is now just inside liquid. Okay. So force acting on the bottom by liquid upwards, force on the bottom and force on the top. So take it as Ft. See here what I am doing. Force acting on the top. That is equal to pressure of atmosphere into cross-section area. This is now downwards. Force acting on the bottom by liquid. See here what is the pressure? Pressure at depth H. That is equal to P naught plus H rho G or rho L. Rho L stands for density of liquid. Okay, this is the pressure at the bottom of the cylinder. that pressure into area. This gives us a force acting by liquid on the bottom of the cylinder. Okay. Now net force by the liquid, that is equal to net force by the liquid, that is equal to force on the bottom minus force on the top. See what we get. P naught A, P naught A gets cancelled. Remaining is now, remaining is now, rearrange that A into H into rho L into G, right? So A into H, volume of cylinder into density of liquid into G, which is nothing but weight of the liquid displaced. Okay. So buoyancy force is equal to weight of the liquid displaced. And you can see this force is because of the pressure difference. We can see here, this is nothing but pressure difference. That is a pressure at the bottom minus pressure at the top into cross section area. So this is because of the pressure difference. And this pressure difference is because of gravity. We can see this is now P at bottom minus P at top, that is equal to H rho L into G into A. We can see this pressure difference is because of gravity. If there is no gravity, then there is no pressure difference. That means buoyancy force is because of pressure difference, which is because of gravity. If there is no gravity, then there is no buoyancy force. Okay. And here, to make calculation simple, we have taken here cylindrical body. In fact, suppose if you take a body having shape like this, now in this case also we get same result. But the only problem is making the calculation is difficult. Okay. So like this, we cannot make calculation. And you can see the advantage of Archimedes principle is we can find volume of a body which has a regular shape. Suppose if you take cylinder, we can find volume pi r square, or you can say cross section area into its height. If you're taking a cube, right? But if you're taking a body which has shape like this, we cannot find volume by making any kind of formula. In such a case, by using now this Archimedes principle, that means if we immerse this body into the vessel, and if you observe how much volume of liquid is displaced, so volume of that displaced liquid is equal to volume of this body. So without using any formulas, we can find volume of a body in a simple way. That is the advantage of Archimedes principle. Okay. Right. Let us see simple problems based on buoyancy force. So focus once the statement here. When a body is immersed in a liquid, completely or partially, it experiences a force equal to the weight of the liquid displaced. Okay. Right. This force passes through the center of gravity of the displaced liquid. It is passing through the center of gravity of the displaced liquid. Okay. That means the center of gravity of displaced liquid may not coincide with the center of gravity of the immersed body. Right? Okay. Now see simple questions basing on this. So the first one, a body of mass 1 kg, specific gravity 2. Specific gravity means density of the body upon density of water, right? Is dropped from the surface of water. Find the time taken by the body to cover a distance of 10 meter in water. Also find average velocity in the same time interval. So given specific gravity 2, dropped from surface of water. So time taken by the body to cover a distance of 10 meter. Let us see how to start. Right. First of all, see the given data. Mass given 1 kg. Specific gravity 2. That means density of the body upon density of water. That is 2. And we know density of water is 1 gram per cc, right? From this, we can see density of body is 2 gram per cc, or you can say 2000 kg per meter cube. Okay, so released from surface of water. Suppose this is now vessel. This is surface of water. Suppose depth is now, that is given how much? It is not depth actually, to cover a distance of 10 meter. Okay, nothing wrong in this. Let us take a vessel which has depth 10 meter. What is now time taken? If body drop from surface of water, time taken by the body to reach bottom of the vessel. Okay, drop from here to reach bottom of the vessel. Also find average velocity in the same time interval. Let us see. So first focus, what is net force acting on the body? So net force acting on the body. So first thing, density of the body 2 gram per cc or 2000 kg per meter cube, right? Okay. So let me calculate net force. So net force F net, that is equal to mg, that is weight, minus buoyancy force. Buoyancy force B, mg. mg means volume into density of body into G. Buoyancy force, volume into density of liquid into G, because it is now completely immersed. Okay, see how much it is. I am taking this entire one outside, mg outside. See what else left? 1 minus rho L upon rho B. See carefully. We have taken rho, density of body, and G outside. So V and G, V and G. Remaining is now rho L upon rho B, right? Now see what is acceleration. Acceleration is equal to net force by mass. So G into 1 minus rho L upon rho B. Now in this case, density of body is more than that of water. So this value is less than 1. That means A value positive. That means body moves down with acceleration, or it moves down with increasing speed, right? Substitute values here. G 10, 1 minus density of liquid. Density of water is how much? 1 gram per cc. It is 1000 kg per meter cube upon density of body 2000. Or directly you can write here 1 by 2, because specific gravity is 2. Then reverse of this is 1 by 2. Okay. So 1 minus 1 by 2, it is 1 by 2. So 10 into 1 by 2, it is a 5. So 5 meter per second square. So body is moving down inside liquid with an acceleration 5 meter per second square. It is a constant. Okay. Now it has to cover displacement 10, starting from rest. So I'm writing here U0, acceleration known 5 meter per second square, displacement, that is a 10 meter. So time taken how much? That is now very simple question, right? So I can use here equation S equal to ut plus half a t square, u 0. So here I'm writing directly S equal to half a t square. S is a 10. Half a value 5 t square. 5 here 2 times 2 to 4. So t value 2 seconds. Now check once. So 20 by 5, 4. T square 4, t value 2. It takes now 2 seconds, right? Now he's asking what is average velocity. Average velocity means we have to take now. Definition is average velocity is equal to displacement by time interval. Displacement, it is how much? 10 meter upon time taken, it is 2. It is how much? 5 meter per second. Okay. Or we can take same thing as, we can do one thing. Just before touching the bottom of the vessel, see velocity how much? Velocity, it is equal to A into T, right? U plus AT, U plus AT, U value 0, A value 5, and T is now 2 seconds. This is now 10. So just before touching the bottom of the vessel, velocity 10. Since acceleration is a constant, that means velocity is changing linearly. So whenever a quantity changes linearly, its average value will be initial value plus final value by 2. Using that logic here, average value equal to initial value plus final value by 2. It is now 5 meter per second. Okay. Like this, we can expect many questions basing on kinematics. Okay. Let us see one more question. So here you have to keep in mind acceleration. With what acceleration body moving down? That is g into 1 minus rho L by rho B. Okay. Right. See next one. A body of mass 2 kg, specific gravity half is released from the bottom of a vessel. It is filled with water up to a height of 5 meters. Find the time taken by the body to come to rest temporarily. Also find the distance of the body from the bottom of the vessel when it comes to rest temporarily. Almost same as the previous question. The only change is now it is released from bottom of the vessel. Okay. Right. First of all, see the given data. So it is given that vessel filled with water. So up to a height of 5 meter. Liquid is up to a height of 5 meter. So we are releasing a body from the bottom of the vessel. This is a body. Given specific gravity means density of the body upon density of water is a half. It means density of body is now less than that of water. That means density of body is now half gram per cc. Right? Right. Next. Mass. Mass is not required. Now see what is asking. Time taken by the body to come to rest temporarily. So first focus, same as the previous problem. First take net force. So it is moving up. Moving up means buoyancy force must be more. Buoyancy force upwards, gravitational force downwards. If buoyancy force is more than that of gravity, than that of gravitational force, then only it moves upwards. So net force must be buoyancy force minus gravitational force. Buoyancy force, volume of the body, density of liquid into G, minus volume of the body, density of the body into G. Again, I am taking mg outside, remaining is now density of liquid upon density of body minus 1. Now see what is acceleration. Acceleration equal to net force by mass, right? It is G into rho L upon rho B minus 1. Okay. See, previous one and this one both are same, right? The only change there we got 1 minus rho L by rho B. It is rho L by rho B minus 1. That is the only change. Means in the previous problem, acceleration was downwards. Now acceleration is upwards. Okay. So G value 10. Rho L by rho B. How much? Rho B by rho water is 1 by 2. If you take reverse, it is 2, right? It is now 2 minus 1. That means inside liquid acceleration is 10 meter per second upwards. Sorry, 10 meter per second square upwards, right? Now question is just like initial velocity 0 because released from rest. Initial velocity 0, displacement 5, acceleration 10 meter per second square upwards, okay. See, by what time it reaches now? Surface of water, okay. So T we want to calculate. So we can take from this S equal to ut plus half a t square, u value 0. So S equal to half a value 10 t square. So here 5 times 5 gets cancelled. So t value 1. That means it reaches now surface of water in 1 second. But we want to calculate when it comes to rest temporarily. Now see what we can do. When it reaches surface of liquid, its velocity equal to a into t. A value 10, t value 1. Means it reaches surface of water with a velocity 10 meter per second. Its velocity how much? 10 meter per second. And once the body comes into air, now the only force is gravity, which is downwards. Now question is just like, this is initial velocity, vertically upwards. Acceleration is now 10 meter per second square downwards, right? Then time taken to come to rest. Let us take this as T1, okay? Now from here to to come to rest. So question is just like projecting a body vertically upwards with a velocity 10 meter per second. What is now time of ascent? Okay. So time of ascent that will be equal to how much? U by G. So 10 by 10. 1 second. That means time taken to come to rest temporarily. It is T1 plus T2. That is 2 seconds, right? And here we have to find one more thing, that is distance of the body from the bottom of the vessel when it comes to rest temporarily. And once we know velocity, see what is this distance that is given by, so take it as this is equal to how much? V square by 2g, that is a 10 square. 10 square by 2g. 1 gets cancelled. 10 by 2, 5. This is equal to how much? 5. This is a 5. This is also 5. So distance of the body from bottom of the vessel is equal to how much? 5 plus 5. It is a 10 meter. So like this, we can expect questions based on kinematics. Okay. So you have to keep in mind while moving upwards, its acceleration will be okay. That means if density of the body is less than that of liquid, its acceleration will be upwards. Okay.